In this video, we're going to learn how Docker creates containers and how Docker also isolate processes. Now, before we go on this video, I need you to understand something, that creating containers or isolating process is not done by Docker itself. Docker relies on some of the Linux capabilities, some of the Linux features for it to be able to create containers and also isolate our process as we may see it. Now, in this video, we're going to go into some details on how that is being done, and also I'm going to understand some of the Linux features that enables Docker to isolate processes. Now, without wasting more time, let's jump straight into it. Now, for the evolution of Docker and the idea of isolating processes, now what actually happens? Now, before then, normally when we want to deploy our applications, right, before the rise of virtual machines, when applications are being deployed, we tend to deploy all the application on one operating system, right? So we have like Nginx running on the same host. We have an application written in Python running on the same host. We have another application running in Node.js on the same host, and all of that. And all of these applications have access to the underlying resources like your CPU, your RAM, your storage, and also networking device or networking component. Now, what usually happens is that each application, send a request to the underlying operating system or to the kernel to request for resources, and then the kernel replies back and grant access to the resources. It can be the process or the application wants to open a file or want to write to disk, and all those are handled by the Linux kernel through the syscall. So the syscall is the process whereby an application running on the user space make a request to the underlying infrastructures to get resources. But now this process led to so many concerns, because as you can see, each of the application are accessing the same resources, and in some cases, one application might interfere with another application. Now you can see that in a situation whereby one application is consuming more resources than the other, that can lead to starvation of other resources. Now you see that, for instance, a Python application can be, maybe due to some misconfiguration, or to some application error, it might be consuming more memory, right, than the others. And because of that, the other application might be crashing or might be having issues and all of that. So you can see that there is, constant competition for the underlying resources, because there's no confinement. So anyone can use as much resources as it can. And in most cases, one application can even hold on to some resources like CPU and all of that. And that is not an efficient way of running application. And on top of that, all the applications have the same, file system. They have the same, they can see the same file system and all of that. And sometimes one binary of the application, might be conflicting with another binary. Let's say, for instance, one application needs maybe Python, a specific Python version, and the other application needs another version, right? Now, this can lead to misconfiguration, or this can lead to inconsistency, whereby one application needs a specific version while the other needs another version. And because of that, you need to start thinking of a way on how to install a specific version of Python that will be compatible with both applications. And as you can see, this is not an ideal situation that you want to find yourself, because you need to start doing more research, and it's going to lead to more overhead. And because of that, we now have another model whereby all the applications are deployed on their own separate host. Now, all the applications are now deployed on different hosts. It can be a virtual machine, it can be a bare metal, whatever host all of them are running is still the same principle, right? And then we now have Nginx running on its own, Node.js running on its own, Python application running on its own. They have their own hardwares and all of that. They can access their own memories and all of that. But these also have an issue. Now, the issue with this is that this can lead to... the issue with this is that there's management overhead. Now you can now see that you now have more than one server or more than one virtual machines or hosts that you now need to you take care of, like patching, and all of that. And number two, there is resource waste, because sometimes you might not be utilizing a specific host up to the maximum point, because some application might just be needing a fraction of the RAM or a fraction of the CPU, and stuff like that. And because you are deploying just one application in a full operating system, that can lead to resource waste. And thirdly, there's slow startup and scaling. Now, trying to scale those applications is not as easy as you may think, because you need to consider the booting of the operating system. Let's say in the situation whereby you want to scale the application that is running your Python application, you want to scale it, using a full virtual machine to scale, is not an ideal situation, because you need a fast scaling whereby your application is spin up as fast as possible. But with virtual machines or with a full operating system, you need to load the kernel, boot everything into the operating system and all of that, which can lead to more time, right? So that is one of that drawback. And the last one is higher cost. Now, if you compare running your application on one host, compared to you running them on a separate virtual machine, obviously running them on separate virtual machine is going to cost you more than running them on one host. So these are some of the drawbacks. This was what led to the isolated process. Now, instead of us now running the application in different hosts on different servers, because we want to avoid all the application interacting, we want to avoid all the application for not interfering with each other process, each other file system, or not consuming more resources than expected. Now the ideal of isolated processes now came into place. Now the idea here is that we cannot have all these applications running on the same host, right? We cannot have all of them running on the same host, but we also want to isolate them. So each of the application now have its own file system, its own resources, its own network interface, and everything that a usual application can have on a specific hardware. Now, you now see that Nginx has its own file system, resources, and the resources is shared from, let's say, a CPU. It has like a fraction of the CPU to itself, while the Python application has a fraction of the CPU to itself. The Go application has a fraction of the CPU to itself. It's just like that. And each of these resources are confined to that specific process. Now you can see that a specific amount of CPU, right? A segment of the CPU is assigned to the Nginx process running here, in order so that when the Nginx wants to use more than that, it is not allowed, because a fraction of it has been assigned to it, and it is only expected to use up to that amount, and nothing more, and nothing less. Now, this led to huge improvement, because we now have all our application running on the same operating system. We cannot manage them, right? We cannot manage them in one place, lesser cost compared to you running them on different operating systems, on different hosts. And, that led to a less overhead, right? And this is what bettered Docker and some of the, technologies that isolated process. And this is how it works. Now, this isolated process is not possible without the Linux features, without some of the Linux features and some of the Linux capability. And that is what we are about to go into now. So you might want to ask, how processes are isolated in Linux? Now, in Linux, there are two major features that helps in process isolation. And the first one is the control groups, and the second one is the Linux namespaces. Now, the control group is just the Linux features that helps us to confine, to restrict resource limit on a process. Now, we've seen here that all of the application, have a specific fraction of the resources, like a fraction of CPU, RAM, storage, and all of that to that specific resources. Now, how do we now enforce that resources to a specific process so that that process cannot use more than that? And that is what cgroup does. So cgroup, which is known as a control group, is the Linux feature that helps us to enforce limits, that helps us to enforce resource limit to a specific process. Now, this now lead to more improvement, whereby more resources cannot consume more than expected or more than what has been assigned to it. So it only uses what is given to it and nothing more. And also, the second one is the Linux. Is the Linux namespaces. Now, the Linux namespaces is what does the heavy lifting of isolating the process, right? So the Linux namespaces isolate the process in various ways. It isolates the process from what it can see, right? So what does that mean? So we now have different Linux namespaces, right? We have the first one, which is the process namespace. It's the process namespace, which is for process isolation. Now, ideally, if all the applications are running on the same operating system or they are running on the same host without any isolation, right? Or each process can see another process, right? Because they all have the same process tree. This process can interfere with another process because there's no isolation. So number two, network namespace. Now you can isolate a process from seeing other process, but without the network namespace that isolate the network, they can still be using the same network interface, the same network route. Now, with the network namespace, we cannot isolate that process from the host network. So each process now have its own network. So when you run your IP, and all of that, the network route, the interface, and everything is different from the one on the host. The third one is the IPC namespace, which is inter-process resources. Now, this namespace is what isolate the various inter-process that run within a process. Now, you can see one process having some other shared process within it. So with the IPC, each of these processes are isolated from the host process and all of that. The fourth one, which is one of the most important one, is the mount namespace, which helps to manage file system. Now, if all the applications are running on the same host without any isolation, they all share the same file system, right? The binaries and everything, the Python versions and everything are the same, right? And that is not a good way to run your application, because one application might be writing to a specific file while the other can be writing to the same file, which can lead to conflict. But with the isolated process, whereby we now have different mount or file system, each of these applications are now isolated. They cannot have their own file system to write to a specific version of binaries, of libraries, and everything. So we have now succeeded in isolating that process, not just on the process level, not just on the network level, not just on the process level, but now on the file system level. So we can now see that different applications, all the three applications, your Nginx, your Python application, your Node.js application, now have their own different mount namespace or different file system. And the fifth one is the UTS namespace, different host and domain names. Now you can now see that the name of your container or the host name of your container is different from the host name of the underlying host. Now, this is different host name and all of that. But with the normal process where there's no isolation, all the application assume the same host name, which is the host name of the computer or the host name of the server that they are running on. And the last one is the user namespace. Now, the user namespace is what isolates the user, of a process from the user on the host. Now, if there's no isolation, if there's no user isolation, a root user on a process, running on a container or running on an isolated process is the same is the same root user on the host. And that is why the user namespace is very, very important, right? And the user namespace is what separates a user on the host from a user on a process. Now, a process might be running as root, but might not be a root on the whole system, right? And that is what the user namespace does. So you can see that all these namespace are just technologies or features that helps us to isolate different parts of a process from the underlying host. Now, if you want to isolate them from the underlying host, indirectly, we are not trying to isolate them from other process, because if they are isolated from the host, then there's every chance that they are isolated from other process, and we cannot run different process. And one thing that you need to understand is that one process running on an isolated environment thinks that it is the only one running on that application. They cannot see anything outside of what has been assigned to them and what has been confined to them. So this is how the Linux namespace work. So with that, this is where Docker comes in. Now, trying to do all of these namespace, trying to create all these namespace for a process, trying to do all of this manually is not an ideal way, because you need to, there's so many things that goes into creating these namespaces, isolating them, creating the cgroups and all of that. It is not one of the best thing to do, from a manual point of view. And that is what Docker solves. So Docker is a technology that helps us to isolate our processes in a form of containers, right? And these containers under the hood leverages those Linux features like namespace and cgroups. So when you run a Docker container, under the hood is creating those cgroups, and it's also creating some of those namespaces, right? And there's one thing you need to understand, that when Docker creates a container and create these namespaces, there is one particular namespace that is not created by default, which is user namespace. And the reason is because when you isolate a user, on the host from the user on the container, so many things might not work, right? So many features might not work. And because of that, by default, Docker does not create a user namespace. It still uses the one on the host. But other processes like your mount namespace, your process namespace, and all of that are created by default when you run a Docker container. So how does a typical process, or how does a typical Docker process looks like when you want to create a container? The first thing is, when you run your Docker run, right, it sends a request to the Docker D. So your Docker D is the Docker daemon, right? It's the Docker engine that does all the heavy lifting. And then the Docker D passes that request to container D. So your container D is the main container runtime, that runs the container, that pulls the image, that spin-ups, that pulls the image, and, run your containers, right? And then container D passes the request to the run C. Now, the run C is the low-level program that, creates the namespaces, right? That creates the C group, set up the file system, and all of that. So when container D pulls the image, maybe like the base image to run the container, it sends it to the run C. The run C under the hood create the namespace, isolate, create the mount namespace, the process namespace, the UTS namespace, and all of that, and then also create the C group, right? And after all of this, it runs the entry point. Now, the entry point is the main command that is going to spin up the process, that container needs to run on. So this is how it typically looks like. Now, all of these are just theory and the concept behind how container works. Now, before we call it a day, let's do some hands-on demo to understand how all of these work under the hood. Now, so I am here on a Linux machine, an EC2 instance, and I just want to show you guys what the namespaces looks like, and also how Docker creates those namespaces. So I'm here and I have Docker installed, and let me just show you that by running Docker ps. As you can see, Docker is installed in this operating system. Now let's run a container and see what gets created under the hood. So I'm going to run an nginx container, Docker run, nginx, and then we're going to see the image are being pulled. Then let's run Docker ps. Yeah, so we see a container running already, which is nginx. Now this nginx is running as an isolated process. Now, how do we confirm that, right? Now, on the host, which is what we currently are now let's check or let's confirm the process ID of this engine is running here. We can do that by running sudo ps aux and hit enter. And then we can see all the processes running, and we just want to get the one for Nginx, right? So we're going to fine tune our search to just that Nginx. So let's do that. We're going to do sudo pus like this, and we are going to grep grep Nginx and hit enter. As you can see, this is the main process ID. Let me clear the screen to make that clearer. And this is the main process that spawns the Nginx process, right? This is 3625. Now we can see that this 3225 is the main Nginx process. Now let's copy that ID. Now, in order for us to confirm the namespaces that was created by this process, right? Because from a previous lecture, I said that when you run a Docker container under the hood, it's going to create, it's going to create namespaces, right? Because we also understood that Docker container are just like an isolated process. Now, how do we now confirm that namespaces has been created when we run the Nginx run to run, when we run the Docker command to run Nginx? Now, we can do that by running the command using sudo ls-ns-p followed by the process ID and hit enter. Now, if you run this command like this, you're going to see all the namespaces, right, that has been created by Docker when we run docker run Nginx. Now, you can see that it's created, the mount namespace, right? You can see the mount namespace. You can see the UTS namespace. You can see the IPC namespace. You can see the PID namespace. You can see the cgroup namespace. There's also a namespace called cgroup, but it was recently, added to the Linux channel, to the Linux kernel or to the Linux feature. I didn't talk about that, but it's almost the same concept. Also, we also have the last namespace, which is the network namespace. Now you can see that all of them has a different PID. You can see that the PID is, the same as the PID of the process running on the host, right? You can see 3625, 3625, 3625, and these are the namespaces created. But you also understand that, you also observe that the user namespace and the time namespace is still the same as the host namespace, right? You can see that the time namespace is, the PID is 1. The user namespace is 1, which means that the user namespace of the host is still the same user namespace that the container or the isolated process is running on. And that is why I said in my previous lecture that by default, Docker does not create a new user namespace. It simply uses the one on the host. And that is because there's a lot of complexity, that needs to be factored in when you want to create a new namespace for a container to run it as an isolated process. Now, and also, I also need you to understand the reason why it is a bad practice to run a container as a root user. Now, you can see that the user that the process is running on, right, this Nginx process or the container, right, because obviously it is running as a container. Docker ps. Now, this Docker is a container, which is also a process that you can see on the host machine, right? Now, it is running at its root user inside the container and also a root user on the host, right? Which means that in terms of container breakout, somebody who is a root in the container is also a root on the host machine. And that is why it is a bad practice to run your container as a root user. Now, we've established the fact that when a Docker container is created, it creates an isolated process, and it is the Linux features like the namespace and the cgroup that helps with this isolation. But we can see that by all these namespaces that we can see here. Now, let's do something interesting, right? So let's say we have Docker ps, right? Docker PS, we see that the container is running, right? And normally, when we want to stop this container, we run Docker stop, right, to stop the container. But in this case, we're not going to be using the Docker stop to stop this container, right? We're going to go to the operating system or to the root, to the host process to kill that process and see if this container is going to be destroyed. Because like we said, it is an isolated process running on the host, which means that if you can kill that isolated process, our container should also be killed, right? So now let's grab again the process ID of the container, which is 3625. Now, 3625 is the main process. As you can see, all these REST process, like the worker process, are being spun up, because of the root, because of the main process. Now, let's kill this process, this 3625, right? Let's do kill. We need to add sudo -9, sudo kill -9, followed by the PID. And if we do that, you can see now if you run Docker PS, we see that our container has been stopped. Now, this now establishes the fact that containers are actually processes or isolated processes running on our host. They are still running on the same host, but the processes are isolated from each other. That is what we have been able to establish. Now, let's now understand something, right? Now, how do we confirm? Okay, let's run the container back again. Let's run our container again. So let's go back to like this and run the container. So if we run Docker PS, we see that the container is running. Now, let's confirm something like, right? So if we exec into the container, right? If you do Docker exec IT like this, followed by the container ID and bash to give us an interface, and we run IPA like this, or IPA, this command is not found, but we can install it on this. We can install it. So let's install the IP command and also the PS command on this container to be able to demonstrate some of the features. So let's run apt update to update that, and let's update that. So that's fine. And then let's install the PS command and also the iprat command and hit enter. Waste of a few seconds. So all of that has been installed. So if we run the IP route IP again, now we see this interface, right? Have a close look at this. Now this is inside the container, which is inside the network namespace. Remember I said a container runs on its own network namespace, process namespace, etc. Now if we exit from the container, right, and we run the same command on the host, you can see that we have a different files. We have a different network, routes, different network interface. Now this is the one on the host, and also the one on the container is just, we have just two interfaces, which tells us that the container is running on a different namespace or on a different network namespace than the one on the host, right? And also, how do we do that? Instead of us executing into the container, we can actually do something. We can do sudo ns enter, right? Ns enter. But before then, let's grab the container ID, or the PID of the process of Nginx. So it is running as 3825. So let's grab that, and let's do that. Let's do sudo ns enter. Target is the ID and also which namespace we want to log into, right? Now we want to exec into the mount namespace. Let's hit M and hit enter. Now if we run ls, we're going to see a different file system, right? Now this is inside the container's mount namespace. Now we can now see a different file system, right? Now if we exec from here, right, let's exit from here to the host, and if we run ls, we are seeing a different file system, right? Whatever you are seeing here is the file system that was created, or the map namespace that was created when Docker created that container, and it is different from the one on the host. That tells you that we have containers Docker containers isolate process using those namespaces that we spoke about. So you can see there's isolation. And also, if you also run ls, if you also check into the PID namespace, right? If we do -m like this, this is for process, and this is for the host, and hit enter like this, right? And if we do host name, or let's say host name like this is the host name we are seeing, this which matches the container ID, right? But if we exit from those namespaces and we run host name like this, we can see that the host name on the host is different from the one on the container, which also now confirm that the UTS namespace, right, is different. The UTS namespace isolates the host name of the container from the host name inside the host. Now you can see that there are different isolation, right? And now if we want to check all the namespaces, right, instead of specifying which namespace that we want to exec into, like the mount namespace, the process namespace, the UTS namespace, we can simply just run -a, which tells us that we want to log in into all the namespace of this container, right? And if we hit enter, you will see that whatever you type here is exactly the same thing as you execing into the container. So instead of us using Docker to exec into the container to check the process, we are simply using the native Linux feature, right, to exec into the container, or to exec into the isolated process. Now you can see that we are inside the container, right, as a root user. Now if we come here like this and we run ps aus, right, you can see that the process that we can see inside the container is fewer. We can see fewer process, right, which tells us that the process inside the container is isolated from the process running on the host. Now if we exit from this container and we do ps aus, we're going to see more process, right? And that is how it works. That is how it works, and that is how, under the hood, Docker isolate process by leveraging those Linux features. Now, the last thing for us to see before we call it a day is to understand the cgroups, right? To understand how it enforces cgroups. And in order for us to do that, let's stop our container, right? Let's do stop Docker stop like this, followed by the container ID. And also let's remove it. Docker remove. Now, we said that it is Docker that enforces resource limit. Now let's run a container, right? Let's run a container with these limits. Now we're going to run this container let's call it my nginx, or let's just remove that and leave it like this. We're going to run this container and we're going to specify a limit of 512 megabytes of the memory, and also we're going to run it like this and hit enter. And if we run docker ps, we're going to see that the application is running, the nginx is running. Now, how do we now confirm that? Because we've also established that namespace has been created. Now let's now verify that C group has been enforced, right? How do you now verify that the C group has actually been created? Well, when you come to this directory, so if you do ls s6 like this, and also if you go into the fs file system namespace like this and enter, if you run lx, you're going to see this. And also you can see the C group here when you list what is inside the C group. Yeah. So when you come here like this, you're going to see that there's a C group folder inside the system/fs. Now when you come to this user slice like this is where you see where this is where you verify if a particular resource limit has been applied to a container. And when you come here, you're going to see different different processes or different files here. We're going to see different files there, but the one we are interested in is the system slice. Now, the system slice is where we see the C group that has been assigned to resources, right? So let's clear the screen again, and instead of the user slice, let's use the system slice and hit enter. Now, if you come here, you're going to see different file system alone, but don't get confused, right? You don't get confused. I just need you to follow me as we go through this demo. And now let's confirm our container ID, right? If you do Docker PS again, we see that our container ID is OC9BBB9. And if you look at it, if you look at this ID very well, this is just the short, the short ID identity, and it matches with what we can see here. So this is the container C group that has been assigned to it. Not the C group, but the C group identity. So let's copy all of that. And now let's go back and go into that folder. Let's list that. So if we list that, we're going to see again different files and folder. And the one we are interested in is the memory max, which is this one. Remember that we set the memory max to be 512 megabytes. So we want to confirm if that limit has also been enforced on that process. Now, if we come here and copy it, and so this is a file, so we cannot list the context. We're just going to cut it like this and hit enter. As you can see, this is the maximum memory that has been assigned to it. As you can see, it is 536870912 byte. Now, if you convert this, you're going to have the 512 megabyte that we establish when we run the container. So as you can see, this is how it works. This is how Docker works under the hood. So Docker creates namespaces and also C group to isolate process. So this is how it works. Thank you guys for sticking around to this video, and I will see you in the next video.